So, let us go back to our solenoid carrying a current. We had made this diagram here, a long solenoid, and then there is a current in each turn, and then the current goes, and we wanted magnetic field inside this solenoid, and outside we have taken it as 0. It is 0, but to prove that it is 0 is not very simple. So, I am just taking it that this is 0, and then this small n is the number of turns per unit length of the solenoid. So, if you take a length delta L and see how many turns are there, then delta n by delta L, that is small n. This is number of turns per unit length along the axis of the solenoid, and with each turn you have a current I. And then we want the magnetic field here, and the magnetic field ultimately it will come out to be this, and but we will derive this using Ampere's law. And we need the direction of this B, and that is where we left it, that B can have, in principle, any vector can have 3 components along the 3 coordinate axis. We are using cylindrical polar coordinates with the axis of solenoid as z axis, and then corresponding phi n and s. So, this is how you can write it: Bs s cap, B phi cap, and Bz z cap. So, first let me show that this B phi and Bs should be 0, so that the magnetic field inside the solenoid is only in z direction, and for that we will use symmetry arguments. If you have this solenoid, think of this solenoid, and then all these turns are there, and inside you have a point P, and take a circular loop passing through this P, coaxial with the axis of the solenoid. So, I need magnetic field here, or I am thinking of the magnetic field here anywhere inside the solenoid, and then it is at some distance from the axis. This is at some distance from the axis, you can name it whatever s. Then with this radius s, draw a circle perpendicular to the axis of the solenoid, and on this loop put an arrow here, and I am putting arrow in this fashion that if you see from the top it will be anti-clockwise. So, this is the arrow, and on this we apply, we first let us see what if there is a phi component of the magnetic field along this dl. Can there be a component of the magnetic field which is in the direction of this phi cap? If it is, and if you use this Ampere's law, then B dot dl will be B dot dl vector is anyway dl in phi cap, because that is circular. So, this is phi cap, this is phi cap, this is phi cap. So, dl is anyway in the direction of phi cap, and B dot phi cap will be the phi component of B. So, it is like this. Now, symmetry. You have a solenoid, you have current at the surface, the turns are at the surface, and then at some distance s you have taken a point, say in this direction. You can take it in that direction, same distance s, you can take the same in this direction, same distance s, and that is how you have made a circle. So, if there is a phi component here, there has to be the same phi component here, same phi component here. All these points are symmetrically placed with the solenoid. Each of the point is at the same distance s from the center. This side, that side doesn't make a difference because your turns are circular. So, whether this side or that side, if you go with the same distance s, all these points are equivalent and b phi will be same in magnitude everywhere, and therefore, you can take it if outside the integral. This step is very crucial. People generally make mistake here. Since it is constant, then only you can take it out. If it is not constant, then you cannot take it out. This part is crucial. And now this will be b into 2 pi s. But then the right hand side is mu naught I enclosed. What is the current going through the area bounded by this circle? Nothing, no current. Inside that volume of the solenoid, there is no current. All the current is on the surface in the turns. So, this side is 0. So, this is 0 and therefore, this b phi is 0. So, you cannot have any phi component in the magnetic field inside the solenoid because of the turns. Next, look at this S. Suppose there is an S component. That means I have a solenoid, and then I take a point P, then there is a magnetic field component which is in S direction, going away from the axis or towards the axis. So, if that be the case, once again we will do some analysis. Let us say this is our solenoid, and then these are the turns, here is the point. So, suppose there is an S component and it is away from the axis. This is the axis and there is a component, there is a magnetic field, there is a component here, Bs. This is component in S direction. Good, very good. So, what we will do is, we will make a circle out here, disc out here, and then a disc out here, and make a cylinder. This point is at the curved surface of the cylinder. We are making a cylinder inside this solenoid. There is a flat area on the top, there is a flat area on the bottom, and then there is a curved area, and the radius of the cylinder is this much, this is S, let us say this is S. So, radius of cylinder is S. Height is vanishingly small, even if it is not small, it will, the logic will do. So, there is some height, right, and then if you look at the flux of magnetic field on this closed surface, flux through this area, this is an area and it is a closed area, closed surface. How is the closed surface made? The top surface of this cylinder, plane surface, the bottom surface again a plane surface, circular disc here, and in between here you have this curved surface of the cylinder. So, you have this curved surface, you have top surface, you have bottom surface. Now, see what happens to this S component. If there is an S component and if it is away from the axis, everywhere it will be away from the axis on the curved surface. Imagine this geometry. Imagine this geometry is 3-dimensional figure. I am making it on 2-dimensional. So, you will have to imagine in space. So, you have this cylinder here, you have a cylinder here, and then there is a curved surface, and here if there is a S component that is going perpendicular to the curved surface, and if you take dA there, the dA direction is also perpendicular to that curved surface. So, B and dA will be in the same direction, S component. So, here you will have Bs into dA, here, dA is in this direction and magnetic field in this component in this direction, S direction, BS, so B dot dA will be BS dA here. If there is a Z component of magnetic field, then the Z dot dA is 0 on the curved surface. But B dot dA may be non-zero or will be non-zero on the top surface and the bottom surface, right. So, you have this top surface. If there is a BZ, good, there is a BZ out here, and here the dA is also in this direction, dA is also in this direction, and therefore this B dot dA, when you do B dot dA, both are in the same direction, so you will have B into dA on the top surface. So, this will be BZ into pi S square if you integrate on the top surface, and positive, but lower surface, the magnetic field will be same. Once again, geometry, it is a long solenoid, so the magnetic field here is Z component, here it's same as here, same as here, same as here. It's a long solenoid. You have current, you have length of the tube in this side also, large length, and that side also. So, this point and this point has no difference, and therefore BZ is same, but dA is opposite. This BZ is same as this BZ, but then dA is opposite, because dA is always outward normal. If you have a closed surface and you are trying to do this flux calculation, then the area vector is outward normal. So, here you will have negative, on this you will have BZ pi A square with a negative sign, and this will not contribute total flux. BZ will not contribute total flux. B phi is already 0, and BS, it is BS, then it is everywhere positive, BS, because BS is contributing here, here, this curved surface, here, here, and everywhere you have normal, outward normal, and BS in the same direction. Therefore, this BS will be positive. But this cannot be for any kind of magnetic field. Divergence of B is 0, and divergence of B implies that if you have a closed surface and you calculate this flux, this has to be 0. That is Gauss divergence theorem. That is Gauss divergence theorem. B dot dA is equal to divergence of B and then d tau. If it is a closed surface, it encloses a volume. On that volume, you integrate this divergence of B, d tau, and since divergence of B is 0 everywhere, so this has to be 0, and therefore this B dot dA, flux of magnetic field through any closed surface in any condition, has to be 0. This cannot be positive, this cannot be negative. So, your S component cannot be towards the axis. So, there is no S component, the entire field is in Z direction. So, these preparations are to be done before we actually apply Ampere's law and write what is the magnetic field. Alright. So, let us do that. Now, we know B phi is 0, BS is 0, it is only BZ, and the task is to find the value of that BZ. Alright, so we again draw a somewhat bigger diagram so that we can do our drawing better. And remember, these turns are tightly wound. I am showing it like a gap there, but they are tightly bound, they are almost touching with each other. The wire has to be some insulation on its surface, so that there is no side current going from one turn to the other turn, but nevertheless we assume that the wires are thin and they are insulated, some insulating. This paint is there, enameled wire for example, which you use in transformers and all those things, and then the windings are close to each other, the turns are almost touching each other. So, that is the kind of solenoid. and we want the magnetic field here at some distance s from the axis, and we know that the magnetic field is in z direction. That is known, that we have established, that magnetic field everywhere inside will be in z direction. So, what we will do, we will make a rectangle, and the rectangle will be taking this as a point on the line, draw a line here inside the solenoid parallel to the axis of some length L, and then draw a parallel line outside the solenoid, same length L, and then join these edges. So, you get a rectangle. Okay. So, this line is inside the solenoid parallel to the axis, and then outside the solenoid again parallel to the axis, and then join the edges and you get this rectangle. Put an arrow. This is a closed loop. This is a closed loop. On this closed loop, apply Ampere's law in integral form. The Ampere's law in integral form is B dot dl on this closed loop. This should be equal to mu naught times I enclosed, current enclosed. Now, here you have to think of little geometry once again. B dot dl is simple to calculate, left hand side is simple to calculate. The magnetic field here, it's same as magnetic field here, same as magnetic field here, same as magnetic field here, because it is a very very long solenoid. So, the fields will be same. If you go up or down, does not make a difference. Here the field is in z direction, dl is horizontal, and therefore, the dot product will be 0 here. Outside there is no magnetic field, and therefore, no question of this B dot dl, and inside once again on this part the field is vertical, dl is horizontal, the dot product is 0. So, the entire on this entire loop, when you do, contribution will come only from this arm of the rectangle, and that will be equal to B into L. B is the magnitude, same here, same magnitude, and into this L, that is this left hand side. What is current enclosed? What is the current going through this rectangle? What is the current going through this rectangle? So, let me do something. So, suppose this is your solenoid, the turns are going like this, it is a long tube, let us say, and then everywhere you have these turns, currents are going this way the currents are going, and then we draw a line which is inside the solenoid parallel to the axis, draw a line outside the solenoid parallel to the axis, and then make rectangle. So, suppose I take this paper here and put this paper like this. So, perhaps you can imagine that this is the line outside the solenoid, and then parallel this line is going inside the solenoid, and this upper edge is anyway joined. I have not torn it here, and the lower end is just imagine that half the rectangle is outside and half the rectangle is inside. And now tell me, how much is the current passing through this rectangle, coming from one side of the rectangle, crossing the rectangle, and then going on the other side? So, yes, very much the current is coming like this, and then it has to cross this rectangle and then go this side. every turn has to cross this rectangle and then go on the other side. Every turn has to cross the rectangle and then go other side. So, how many turns are there which are crossing this rectangle? If this length is L and per unit length of the solenoid along the axis, the number of turns is small n. So, if this length of this line is L, small n into L, these many turns are crossing this rectangular area. And remember, this solenoid is long, our rectangle is over here, but the solenoid is there. So, the current is going this way, the current is going this way, a turn is going this way, a turn is going this way, a turn is going this way, each one is crossing this rectangle. Alright. So, you can see that the current crossing this rectangle will be how much? N into L into I. These many turns, and each turns carries a current I. These many turns are crossing this rectangle and each turn is carrying this current I. So, this is the total current enclosed, mu naught, and hence B is equal to mu naught N I. Your very familiar expression for magnetic field inside a current carrying solenoid. Now, the interesting thing is that you do not have a very long solenoid of kilometers. You always work with solenoids of few centimeters, 10 centimeters, 20 centimeters, 30 centimeters, 50 centimeters, half a meter. Normally, we work with those kind of things. So, there how do I write what is the kind of magnetic field? So, it is very interesting to know about it. This I am quoting from a book by Purcell, wonderful book, Berkeley series of physics. And then this is a radius R, solenoid, this is a solenoid, this is a solenoid, tightly wound and everything, but then okay, fine, here you have battery etc. So, current is going this way and then current is coming this way, and that is all. So, this is the solenoid. Each turn carries a current I, that is fine, each turn carries a current I, that is fine. You have n number of turns, very tightly wound, all those things are there, only thing that length is finite. And Purcell takes the example in which this whole length is 4 times the diameter or 8 times the radius. So, 4 times the radius on this side and 4 times the radius on this side. This is that radius. Alright. So, this is the solenoid, and then he calculates, this is easy to calculate using our Biot-Savart law formula on the axis. If you are on the axis, then you can use that expression from each turn, what is the magnetic field at the axial point, and from there you can do that. And on this they plot a graph, and here is the magnetic field, and this is this direction, and then if you see the graph in Purcell, it's almost constant, till this is 4r. So, here it will be half, and then the magnetic field will almost constant, and then will fall like this, and then will fall like this. So, even if it is not a long solenoid, is not a long solenoid at all, just 4 times the diameter. The length is just 4 times the diameter. If the diameter is 5 centimeter, this is 20 centimeter. If the diameter is 2 centimeter, it is just 8 centimeters coil. But you can see that in the middle region, and middle means this is the end, and if you go little bit inside, this is the end, and if you go little bit inside, not even one radius, half radius or 3/4 of a radius, and then you see that visibly it appears as if it is constant. So, inside the solenoid it is still you can say that it is constant magnetic field mu naught Ni, provided you are not very close to the ends. If you are say 2 radius inside or 3 radius inside, you can very safely use this formula mu naught Ni. So, we will stop here.